Section 1.1, Introduction. The purpose of this section is really just to set the stage for what we're going to do in the future. There's no solving of differential equations in this section, but rather we focus on explaining what differential equations are, showing you some prototypical examples of differential equations, showing how we classify differential equations according to various factors, and describing where they arise in real life, how they come about in real life. So first off, what is a differential equation, or a DE for short? A differential equation, in contrast with an algebra equation, is an equation involving an unknown function and at least one of its derivatives. So an algebra equation would not have a function as its unknown, and it definitely would not involve the derivative of that unknown function. In an algebra equation, the unknown is a numerical constant or numerical quantity rather than a function. A very basic example from Calculus 1 would come from population models. Suppose that we're modeling some type of population, whether it be fish in a lake or deer on an island or bacteria in a culture, that says suppose a population grows at a rate proportional to the population itself. So in other words, the more deer that are on the island, the faster the deer are going to reproduce. So here we have a population, we'll call it capital P. It occurs at a time we'll call little t, so P of t would be a population at time t. And the differential equation, which is just a calculus rewriting of this sentence, we're just mathematizing this sentence into derivative language, we would say that the rate of change of the population, dp dt, is proportional to, so is equal to a constant times the population itself. Here, k is a constant called the constant of proportionality. So notice this is a differential equation, and the unknown p, the unknown would be the population at time t. Our goal would be to solve to get a formula for the population at time t. We fill in this blank with a formula for p of t if we could. Right now, that's not our main point. We're really just trying to discuss the nuts and bolts of what are going on rather than trying to solve them. It's important to realize here that time t is the independent variable and p is the dependent variable. So for example, if we were going to graph whatever the solution to this is, if we were going to graph it, we would have t on this axis and p on this axis, and then y would be p of t. Okay, another example that comes about in basic physics is the so-called spring mass system, or motion of a spring mass system. So the idea here is suppose that you have a platform, you've got a spring with a mass attached to it, and it's just sitting there at equilibrium. We'll say that this dashed line is the equilibrium position, and then it moves up and down relative to that equilibrium position, sort of like a tennis ball on the end of a slinky. So I'm just making up a differential equation here, although this would be a potentially realistic scenario, where we have y double prime plus 2y prime plus 3y equals cosine t. Here, t is the independent variable, time. Y is the dependent variable. Here, y would represent the vertical displacement of the mass around its equilibrium. And so we're trying to find its position, which by that we mean its vertical displacement from the equilibrium position. Again, t is the independent variable, so if we were going to graph this, we would have t on this axis and y on this axis. And the graph we would generate would be the position of the mass at time t. Our goal would be to solve for y of t. That's not today's goal, but eventually we'll solve for y of t. And so here the unknown, the thing we're looking for, is y of t. It's a differential equation because it involves one or more of its derivatives, of the unknown function's derivatives. Now, differential equations can become more complicated. I'm not saying that I'm proving this, but if you were looking at heat flow in a thin wire, where you were looking along that wire and you looked at a particular position at a particular time and you measured the temperature in that wire, we'll say that U is the temperature, X is the position, and T is time, then at different points in time and different points in space in the wire, you could have different temperatures. And so the temperature function U of xt, it turns out when you look at heat flow in a wire, that the differential equation which models this, when you look at the physics that are involved, is the partial of u with respect to t is equal to the second order partial of u with respect to x. And so here We have partial derivatives, and this is what makes this a partial differential equation because it involves an unknown function of more than one variable, and so its derivatives are going to be partial derivatives. Here, the independent variables are x and t, so that's space and time, and the dependent variable here would be the temperature. So this is a partial differential equation. We call these PDEs for short. Notice this was an ordinary differential equation. Y was just a function of one variable. The derivatives are ordinary derivatives, so we would call this an ordinary differential equation. Similarly, our very first example, P here is a function of only one variable, and it's T. So the derivatives here, the derivative here that's involved is an ordinary derivative, and so this would be an ordinary differential equation. So this is an ODE, this is an ODE, and this is a PDE. The solution to this is certainly much more complicated because now this is a surface in R3. If we plotted z equals u of x comma t, we would have x on this axis, t on this axis, temperature on this axis, and so we would have a surface in R3. So partial differential equations are a significant sophistication increase from ordinary differential equations, but it turns out that in order to understand partial differential equations, you have to understand ordinary differential equations first. Sort of like in order to do calculus 3, you had to understand calculus 1 and 2. So that's the analogy here between ODEs and PDEs. This course, however, is just about ODEs. So an ordinary differential equation versus a partial differential equation, I just discussed this. This is the topic of this class. Although in the homework, they will give you some ODEs and some PDEs, and they'll just ask you, is this an ODE or a PDE? And you should be able to tell from the context or the nature of the equation. So other ways that we want to classify differential equations, well, one is according to whether it's ordinary or partial. We do want to talk about its order. We're going to talk about whether the equation is linear or nonlinear. For linear equations, we're going to discuss when they're homogeneous versus non-homogeneous. And all of these classifications help us know how to attack the differential equation in terms of solving it. So this is exactly what you experienced in your algebra life. You know, if you saw something that looked like x squared plus 3x plus 4 equals 0, you would say that's a second degree equation, it's a quadratic equation, and you would attack it one way. Versus if you just had x plus 3x minus 2 equals 5, that all is a first degree equation, and that's a linear equation, you would attack it a completely different way. So the order of the equation matters. So let's talk about how we can tell the order of an equation and whether it's linear. And sometimes this is a little bit of a difficult definition for people to wrap their heads around. So let's just jump in and see what happens. So the standard form for an nth order linear ODE, it's an nth order linear ODE if it can be written like this. And I know that could look quite intimidating, but the idea here is if you look at it that y is the unknown, and so we have y prime, we have y double prime, and we just keep counting up all the way until we get to its highest derivative. We'll say that the highest derivative that appears is the nth derivative. And then what's multiplying on the front of those derivatives is just some function. So this is some function of x, some function of x, some function of x, some function of x, some function of x. We've just subscripted these so that they'll match the order. So 1 with a 1 prime, 2 with a double prime. But every one of these can be different functions. The only rules of the game are that this one could not be the zero function, because if it were, this wouldn't really be an nth order equation. This would go away, and it would now be an n-1 order equation. Notice that everything that involves the unknown y is on the left-hand side. And if it does not involve y, it only involves x. If it does not involve y, then it needs to be on the right-hand side. Why don't we look at some practical examples? When n is 2, then we're just going to let n go all the way up to 2. So we're going to get y times a coefficient function plus y prime times a a1 of x. This is the coefficient function for the y prime, plus a y double prime times an a2 of x function. So this could be anything. Any function of x here, any function of x here, any function of x here. Now I'm using the letter x here, but it could be any independent variable. And I'm using the letter y here, but it could be any dependent variable. And so notice that this is the standard form for a second order linear ODE. So if you're given an ODE, it can either be written in that form or it can't. So for example, the spring mass system problem that we looked at was y double prime of t plus 2y prime of t plus 3y of t equals cosine t. Now I know up here we used x's and here we're using t's. I did that on purpose so that we can get comfortable using different letters. But if you just stare at this red equation matches this blue template. If you just, wherever you see an x, you put a t, you can see that the coefficient on the front of the double prime is an understood 1. That's perfectly acceptable. The coefficient on the front of the y prime term is a 2. The coefficient on the front of the y is a 3. The f here is a cosine t. Everything here matches the template. So we would say that this is a second order because it's the second, a double prime is the highest derivative that you see. It's linear because it matches this template. And then when it matches this template, if the f function here is the 0 function, we call it homogeneous. If the f function here is not the 0 function, then we call it non-homogeneous. So this is a non-homogeneous second order, linear, non-homogeneous ODE. Okay? If we were going to look at when n is equal to 1, it's even easier. We just chop off this term, and we would have a1 y prime of x plus a0 of x times y of x equals f of x. So as I just said, if f is 0, f could be 0 or not. If f is 0, we call this a homogeneous equation. If f is not 0, we call this a non-homogeneous equation. Very important, if it doesn't match this template, we do not classify it according to homogeneous or non-homogeneous. So basically the classification scheme is going to be, is it an ODE or a PDE? We're going to see if it can be put into the linear template. If it can be put into the linear template, we should be able to read off its order and read off its forcing function. If the forcing function is 0, then it's called homogeneous. If the forcing function is not 0, then it's called non-homogeneous. On the other hand, if it does not fit into the linear template, then it's called nonlinear. We can still talk about its order, but we don't talk about homogeneous or non-homogeneous. Let's look at some examples. So that very first example that we had, dp dt equals kp, where k is a constant. First, let's try to make it match the template. So remember, I need to get everything that involves my dependent variable on the left-hand side. So I'm going to throw this to the left-hand side. Now it's in standard form, and if I compare this to the first order template, I see that this is playing the role of y prime. My coefficient function is an understood 1. This is my p. What's playing the role of my coefficient function is a negative k. So this does match the template. Because it matches the template, and this is the highest derivative that appears is a first derivative, this is a first order equation. It's an ODE. It's linear because it matches the template, but the forcing function here is 0, so this is a homogeneous equation. So it's a first order linear homogeneous equation. These are going to matter because the way we attack solving the differential equation depends on the category of equation that it is. We're going to treat first order equations differently than second order equations. We're going to treat linear equations differently than nonlinear equations. And we're going to treat homogeneous equations fundamentally differently than non-homogeneous equations. This takes a little bit of practice. You just need to look at a few examples. Let's just run through some. So I know I already have it written here, but if you just ignore this and try to figure this one out yourself, we just did this one. This is a second order, linear, non-homogeneous equation because it matches the template. But what if we do some variations on this theme? So what if we change this cosine x to a cosine y, leave everything else alone? Well, notice now, remember what made it linear is you need to be able to put everything that involves your dependent variable, you need to be able to put it on the left-hand side and it matched the template. If you compare to the template, this does not match this because this needs to be an f of x, not an f of y. So this is still an ODE, it's still second order, but it's nonlinear because of this. Similarly, if you look at this one, now this is okay, this matches the template. But if you stare at this, this does not match the template. I'm not allowed to have a y squared. Everything has to be y, y prime, y double prime. I can't have anything fancier than that. So because of this term right here, again, it's nonlinear. Still second order, still ODE, but it's nonlinear. So what if we look at this and we change the coefficients from a 2 to a 2x and from a 3 to a 3 square root of x, but we leave this as a y prime, and a y double prime, and this is a cosine x. If you stare at this with the template, it does match. When it matches, this is a second order. It's a linear equation. It's non-homogeneous. The coefficient functions are 1, 2x, and 3 square root of x. So see, if you think that it's linear, you ought to be able to read off its coefficient functions, its order, and you ought to be able to read off the f is called the forcing function. The forcing function is either 0 or not 0. You ought to be able to read that off. What if we had an equation like this? Well, first we have to try to put it in the form of the template, so everything that involves the dependent variable needs to be thrown to the left-hand side. So I'll throw this over, and when I do, notice it matches the template. This is a second order linear homogeneous equation. Okay. So the last thing we want to talk about is, where do ODEs come from? Well, one thing is they could be viewed as just purely mathematical objects. You could just say, hey, I wonder if there's any function that satisfies this. Is there any function out there in the universe that when I take that function and I multiply it by 3 and then I add 2 times the derivative of that function and then I add the second derivative of that function, will they all combine to give me just a cosine x? As a pure math problem, you could ask that. These are perfectly valid mathematical objects in that vein. But almost always differential equations arise from modeling some phenomenon of interest. If you're in electrical engineering, it could be circuits. If you're in mechanical engineering, it could be spring mass systems or something involving stresses and strains or heat flow. If you're in biology, it could be population models. If you're in chemistry, it could be the rate of reaction. All sorts of things. In economics or business, it could be the price of a certain commodity changes due to market forces. So really, there's some kind of physical laws that are going on that we want to model using those rules or laws and mathematize them to become equations involving rates of change. And equations that involve rates of change end up being derivative equations, which are differential equations. And in this class, the unknown function will always be a function of only one variable, so they'll be ordinary differential equations. So based on this, you ought to be able to do all of the homework for this section, which is understanding ODEs versus PDEs, understanding the template for a linear equation, knowing the order when it is linear, what the order is, and whether it's homogeneous or not, and then also understanding how an equation can be nonlinear.